Welcome, everybody. Welcome to this February 2025 Discover Us webinar. And today I have the honor to host Kate Keahey. Kate has a joint appointment as senior scientist in the Argonne National Lab and also in University of Chicago. Kate is one of the pioneers in cloud computing, and in this topic, she worked on the Nimbus project that she created, and it's recognized, which is recognized as the first open source infrastructure as a service implementation. Later, Kate has been leading the Chameleon project, which provides a deeply reconfigurable, large-scale, and open experimental platform for computer science research, which will be partially covered by the talk today. And more recently, Kate has been working on in edge computing, which is also the topic of the talk today, as you can guess. And also, I would like to highlight the work that Kate has been doing on reproducibility, with also Camelo providing an excellent tool for enabling researchers to have this reproducibility of their experiments. So with this introduction, I would like to invite Kate to start sharing her slides and starting her talk.
Yeah, so the sharing the slides.
Uh,
Okay, so thank you, Rosa, for a lovely introduction. Thank you, everybody, for coming to the webinar. And today we're going to have a nature talk. We're going to talk about reptiles, and in particular, we're going to highlight chameleon, which is a system. It's not, I mean, it's of course it's a reptile, but it's a system. And we named it chameleon because it's a metaphor. And what is it a metaphor for? It's a metaphor for change. So it's a system that adapts itself to experimental needs that you might have. But in a broader sense, it also is a system that adapts itself to the evolution of science, to new experimental needs that we all come up with. And I'm going to talk a little bit about both how it adapts itself on this individual investigator level, right? So how it might adapt itself, or how you might adapt it to support your experiments, but also how it evolves. In other words, how it changes in order to meet the evolving needs of science. So Rosa already introduced me and explained that I'm a scientist at University of Chicago and Argonne National Lab. But Chameleon is a project that I lead, and it's a partnership between multiple institutions. Two of those institutions are supercomputing centers, so it's Texas Advanced Computing Center and NCAR, which is National Center for Atmospheric Research. They have a supercomputing center in order to run the climate simulations. And our hardware at the University of Chicago is located in ALCF, which is the Advanced Leadership Computing Facility at Argonne. So in addition to those supercomputing centers, the partners, Chameleon's partners, include also RENCI, which is also home to a very interesting infrastructure called Fabric, which is a networking testbed, and Northwestern University, which is home to Starlight, which is another networking infrastructure. So the objective of bringing those institutions, fantastic institutions, by the way, together, is to create infrastructure that will provide supercomputing resources and tie them with high-speed networks. And as I talk about the system later on, you'll see how that works in practice. Okay, so without further ado, as soon as I can get this to work, there we go. This is Chameleon in a nutshell slide that I always start with, and I start with kind of 4 bullets of what a chameleon is. What is the essence of chameleon? And the first one we already talked about. Chameleons like to change. Chameleons are a metaphor for change, right? So it's a testbed that adapts itself to your experimental needs. And in order to support that for computer science research, right? So Chameleon is a platform for computer science research. That's the main thing. That's probably 90% of the work that goes on the testbed. Computer science education, which is also very prominently featured, and emergent applications. So emergent application usage, so non-production application usage, so that means applications that are trying out new paradigms that don't really completely have defined their experimental needs for or their need for computation in their science, and they are trying out various different things. And you'll see later on that's particularly true of this edge to cloud paradigm, right? So many applications right now are testing the waters in how do we do edge to cloud, how do we do AI in edge to cloud. But for computer science research, we're talking about people who design new operating systems and do performance variability studies and maybe work on energy efficiency. It's a very, very popular topic recently. And you can't do this kind of research by submitting jobs to batch schedulers. So first of all, it has to be interactive, and it also requires deep reconfigurability. So, imagine that you're working on power management. You probably need to have access to various components of the node, not just the node itself, but firmware. You need access to deep system features. You may need to install a custom kernel and boot from that custom kernel. You, of course, have to have root in order to make all of that configuration possible, right? So we do deep reconfigurability, allow you to configure resources at the bare metal, right? So think one metaphor is deploying virtual machines, right? So it's kind of like deploying virtual machines, except you're not deploying a virtual machine, you reconfiguring things at bare metal, right? So most of the system is available in this way, but we do virtual machines too. We do virtual machines on a smaller component of the system. It's very, very popular for education, right? Because when students get themselves into their fork exec loop, it's much easier to restart a virtual machine than to, take many minutes that it takes to reconfigure a node on a bare metal level. And then recently, we also started supporting reconfiguration via containers, especially for the edge resources, which are Raspberry Pis or NVIDIA Nanos, which are distributed in the wild. But more about that later. But for now, it's just that we offer makes Chameleon very different from most of the systems that are available to science. It works like a cloud, but a bare metal reconfigurable cloud, right? So not just deploying virtual machines. Yes, we support that too. But you can deploy nodes on, reconfigure nodes at bare metal level. Secondly, we support a great diversity of hardware. From large to small. So like I said, we've got supercomputing centers as our partners. They are connected over a 100G network. They are connected to the Fabric core network reconfiguration testbed. So we support things at a large scale, but we also support edge devices, right? So those are not exactly very powerful computers, relatively speaking, but they are just widely distributed. Secondly, we have investment in great diversity of resources. So we've got different generations of FPGAs. If you're looking at that, GPUs, we've got a whole zoo of NVMEs and just generally speaking, different memory solutions from consumer grade to data center grade type of devices. And then, of course, interesting networking hardware, but then, of course, edge devices and so on. And it's a distributed infrastructure. So the 3 core sites on which most of Chameleon resources are located are, of course, at University of Chicago Tech and NCAR. But we also have volunteer sites that join Chameleon. So we packaged Chameleon infrastructure in such a way that it's easy to deploy. So if you have resources and want to make them available to science, you can join Chameleon by deploying that packaged version of Chameleon infrastructure on your resources and join the system. And we've got sites at Northwestern and University of Illinois in Chicago. And now, quite recently, the National Research Platform out of San Diego joined Chameleon as well. And then we're working with multiple others. Those conversations are not always moving fast because those are volunteer systems. But just to illustrate how things work, NCAR has been a volunteer, and NCAR, in fact, has been the second volunteer site in Chameleon for quite a few years. And they did such an outstanding job of managing the site that we decided to invite them to become part of the system in the next iteration of the system, which is just starting. Thirdly, what also makes Chameleon a little bit different than many test beds is that many test beds are configured using some sort of homegrown infrastructure, right? So this is a very unusual way of providing resources, again, so people develop unusual systems in order to support that. But what we did is we like to be based on mainstream whenever we can, right? There are many, many benefits to being based on mainstream, including robustness and stability, and working with, in our case, a large open source community. So we decided to be mainstream, and therefore we based the system on OpenStack, which I think to many of you may be familiar as the leading open source implementation of infrastructure as a service right now. And of course, OpenStack has a component called Ironic, which supports bare metal reconfiguration. So over time, we've had to adapt OpenStack to meet the needs of our use case. It didn't quite meet the needs of our use case out of the box, right? So what I typically say, a little bit tongue-in-cheek, that we are about 50% OpenStack and 50% special sauce, right? So various things that we added to OpenStack, such as bare metal snapshotting, network stitching, various orchestration methods, just all sorts of integration with Jupyter, access via federated identity, which is very useful for scientific infrastructures, and so on and so forth, right? So we adapted OpenStack in many ways. Some of those things we contributed back to OpenStack. So for example, Chameleon team was a leading mover and shaker in introducing advanced reservations to OpenStack. So that we contributed, that became part of OpenStack. So that's great. But essentially, being based on a mainstream infrastructure allows us to be cheap, right? Because every time we need some other features, chances are that the broader community already thought about that, and we get them by just upgrading. If that's not the case, we develop those features ourselves, but we can make it available to others, which multiplies our impacts, right? So it's a good thing. And from the perspective of our users also, they come to Chameleon, they see OpenStack interfaces. Most of them are already familiar with those interfaces because they're very similar to the commercial cloud interfaces, like what Amazon and Google offers, right? Maybe just a little bit different, but not too much, the same basic model. And if they are not familiar with those interfaces, they also learn about cloud computing, right? So by using Chameleon, they learn how to use cloud, and later on can put on their resume, I'm familiar with the OpenStack client-side interfaces, right? So very familiar, and if not familiar, then it should be familiar, and it's good if it becomes familiar. And then lastly, we promote methods for digital artifact sharing, and I'll talk about this a little bit later as well, but we have integration with Jupyter in order to facilitate packaging experiments. We have a system called Trovi where people can easily share packaged experiments, and we invest a lot in working with community on reproducibility, on education, sharing educational materials to make both science and education, computer science and education, easier on the system. Okay, so this is just a little graphic that shows you on one side is a picture of the first node we ever got, so part of the first rack we ever got. On the other side is a picture of our first rack of Raspberry Pis. The first one dates from about 10 years ago. So Chameleon started, the project started in October of 2014. So the project itself is more than 10 years old. The system was made available in July of 2015. So the system itself is not quite yet 10 years old, right? So this is why I have the little birthday picture here. We were celebrating our 9th birthday a year ago. over that time, we had the privilege of working with over 11,000 fabulous users. I mean, really fantastic. This is what rolls us and makes us roll out of bed every day. Um, we've got users who work on really exciting research and education projects. And every day we get some questions from users about some things that are not yet possible to do. And that inspires us to work on new features and evolve the system. So over that time, these users worked on, at this point, it's close to 1,200 of unique projects, and again, in research and education. And those are unique projects. Chameleon projects very often get renewed. We've got projects that span nearly the 10 years that the system was in existence. And collectively, that community produced over 700 research papers. And you can go to our website, you can see those papers on the website. We're always very proud of the research that our users do and the awards that this research wins for them. So it's a fantastic way. If you ever need inspiration, you can go and look at the great work that our users have done. We also have a blog where we profile our user projects every month. Okay, well, moving on, here's a brief summary of Chameleon hardware. So you can see that we've got two primary sites. NCAR just joined Chameleon in this iteration of the system. So Chameleon got funded for another iteration last year in the fall. So we started phase 4 of Chameleon in October 2024. That phase 4 is going to go for another 4 years, right? So it's going to go till October 28, possibly a little bit beyond that. So Chameleon NCAR is going to become a new site. So far, they have the hardware that they contributed as a volunteer site. Those are ARM Thunder nodes. But University of Chicago and TAC have many different, a zoo of different architectures, mostly Intel architectures, but more recently AMD. AMD became very good at various things. We've got a range of different GPUs on both sides, right? At TAC, we've got GPUs going as far back as K80, right? That's a really old one, but more recently, we've been investing in A100s. At University of Chicago, we have RTXs, which are the gaming GPUs, which are perhaps not as powerful, but there are many of them, and they are very popular for educational projects. And now for phase 4, we already bought H100s, and we're hoping to make them available at TAC, which we will do originally through virtualization, because that just allows us to share those GPUs much more efficiently between various different users. And in phase 3, in the last phase of Chameleon, we added something called Chi at Edge. Chi stands for Chameleon infrastructure. So this is Chameleon infrastructure at Edge that allowed us first to add various edge devices, and then later on allows users to add their own edge devices. A few words about Chi in a box, which Chi, again, is Chameleon infrastructure, is packaging of Chameleon. So packaging Chameleon stands for Chameleon infrastructure in the box. And it packages not just the system, but also its operational model, right? So how to operate the system and so on and so forth. And that made it easy to deploy the infrastructure on all those different volunteer sites. Normally, deploying infrastructure as Chameleon is an extremely complex infrastructure because, of course, it solves a very complex problem, right? So this reconfiguration on bare metal is not that easy to do. But Chi in a box packaging makes that sort of thing easy to deploy on your own site. And we're working with multiple institutions right now to create Chameleon sites at those institutions. And incidentally, it became easy enough that it became possible to create Chameleon sites for various events. So for a few years, we have been working with the Supercomputing Conference. Supercomputing Conference supports student cluster competition, SCC. And we've been working with the Indie SCC, the sort of on-ramp kind of SCC student cluster competition, and people were configuring ephemeral Chameleon sites just to support the competition. So ephemeral Chameleon site, that means a site configured for just several months to support just the competition, just the students for that competition, and then they take it away. So that's interesting that we managed to make configuration of very complex infrastructure, because again, solves a very complex problem, easy enough that it's possible to use it for special purpose type of events. Okay, so we've got this hardware, we've got this wonderful infrastructure, but as a user, what do you see when you come to the testbed, to the system? So we try to support your typical experimental workflow. And if you think about your typical experimental workflow, you form some hypotheses. Now you need to test this hypothesis. So what do you do? So if your research is about, let's say, machine learning, which a lot of research seems to be about these days, right? You need to find some GPUs to test it on, right? So in other words, you need to discover resources. So we provide discovery services that allow you to do that. But then you need to allocate resources. And with GPUs, this could be a little bit problematic because they are very much in demand, right? So if you come to Chameleon and want to get some resources, some GPUs on demand, that's going to be hard because mostly they are going to be all in use by other users. And Chameleon is a very busy infrastructure. We've got about 600, 700 unique users logging in every month, right? So very busy infrastructure. So what do you do? Well, this is where the feature called advanced reservation comes in, right? You come to the system, you look at our availability calendar, which you see when the resources are reserved and when they become available, and you can see that all the GPUs right now are busy. But you can see that if you look a little bit further in the future, a week from now, let's say, oh, here is a GPU that became available. And you can make an advanced reservation for that GPU for a week from now, right? And that GPU, once the start date rolls around, that GPU is going to be there waiting for you for sure. Nobody else will be able to take that GPU. So that's quite useful if you're teaching class, if you're giving a demo, but also it's quite useful for dealing with scarce resources. And you can not only reserve nodes in this way, you can also reserve VLANs, you can reserve IPs, public IPs, right? Make sure that you have enough public IPs for a class, you can reserve that number of IPs. And then once you get access to that allocation, well, you need to reconfigure it. And like I said, most of the nodes are reconfigurable at bare metal. Some of them are reconfigurable via deploying virtual machines. And the edge resources are made available or reconfigurable by deploying containers. And we don't, you can configure your own images, but we provide between 15 and 20 images that are already configured, that we already configured for you. So you can start with those. You can either just simply use them, or you can configure them further. And then once you get the configuration that you want, you can snapshot it. You can snapshot it, you can share it with somebody else, and hey, this is the exact configuration I need for my experiment. Right now, you can start from the same image, and that configuration will pop up for you with no extra effort. And then all this interface to discover resources, to allocate them either on demand or by advanced reservation, to configure them, all those interfaces are available via either GUI, the graphical user interface, via command line interface, right? So you can type commands on command line, or via Python Chi. So we've got a Python Chi library, which means that you can now write a Python program in order to create your experimental environment on Chameleon. Okay, and moving on, one very important thing is Chameleon is not just a system, not just a pile of hardware here and there in various supercomputing centers and networks and configuration of the system, but very importantly, from our perspective, it's a community. It's a community, again, fabulous users who are always pushing what's possible. And over the many years, we collected pictures of our users showcasing their research at conferences, winning awards. Also, that Supercomputing 17 picture is our users getting awards. Working in their labs, participating in competitions, giving demonstrations, and so on, so and so forth. And like I said, every single month we profile one of our user experiments on our blog. So if you want to see what users work on, you can go and look there and see what they do. Okay, and now I wanted to change pace a little bit and tell you about that second aspect of the metaphor for change, right? The first aspect of the metaphor for change was how the system adapts itself to your experimental needs. But now I wanted to give you an example of how the system adapted itself to the evolving needs of science. And so for some time, some years ago, let's say, I don't know, 5 years ago, 7 years ago, more like, we became aware that many of our users were looking at edge computing, at Internet of Things devices, and they were running experiments in network traffic fingerprinting, in biometrics, federated learning. Those were things that they wanted to do. But how do you do federated learning experiment if you don't really have edge devices? Well, you run a simulation or some sort of emulation. But it's not a good look for an experimental test bed. If you want to experiment, the only way you can experiment is by running a simulation, right? It's not a good look. So we were working with users and sort of trying to figure out how can we evolve the test bed to meet their needs, right? How can we add edge devices in such a way that it satisfies their needs? We had kind of two opposing opinions there, right? So most of our users were saying, we want this to look exactly like Chameleon looks, right? We want all the features that we have right now, but on edge devices. And we want to be able to run edge to cloud experiments from one Jupyter notebook, right? One notebook to rule them all. Other users were saying, but edge devices are kind of not like a cloud, right? You don't put them in a data center. We don't want Raspberry Pis and Nanos in the data center. Furthermore, there's typically a reason why they're not in that data center, right? There's a reason for that. And the reason is that they are usually associated with some Internet of Things peripherals, right? They might be associated with a camera. They might be interested with some temperature and pressure sensors, with a GPS system because they are on a bus. The bus is moving, right? So we want that. I mean, that's the whole point of having those edge devices. And they're not server class, so they don't have IPMI interfaces. How are you going to make that bare metal or configurable, right? So out of those two somewhat opposing views came the concept of providing Chi at edge, so Chameleon infrastructure at edge, that will use reconfiguration through container deployment, right? So not bare metal reconfiguration. You're going to be deploying containers, just like you deploy virtual machines on our KVM offering. That is going to have support for some IoT peripherals, but because we can't support every IoT peripheral in the world because new ones are coming up every day, especially in an experimental testbed like Chameleon, right? But it will also give users a framework to add their own peripherals. And most importantly, while we are supporting some edge devices in the data center, right? So we've got some Raspberry Pis and some Nanos and some Orins and some other things in the data center, and some people run experiments on them. We also understand that people want to support those devices in the field. And in particular, very often they want to add their own devices. So many users told us the price is not the barrier, right? The Raspberry Pi can cost you as little as a few bucks. But how do I share this Raspberry Pi, or how do I share my edge infrastructure with my students or collaborators securely, right? So there are all sorts of issues that need to be addressed there, and I'll explain them later, right? But it is an important thing there. So out of that came the concept of a system that supports mixed ownership, right? That allows users where we don't just support the devices ourselves, but we allow our users to easily add their devices to the testbed, but for limited sharing, right? So when people add their devices to the testbed, they say, I don't want to share them with all Chameleon users. I just want to share them with my class or my collaborators, and it's my hardware. And that makes sense, right? So we implemented something called Bring Your Own Device, allows you to add the device to the testbed and share it with others. And so I am going to change pace a little bit and explain to you a little bit about how this all works, but I'll explain it based on an example of how the system is used, or simplified, how Chia-Edge is used, but really a simplified version of Chia-Edge. And here I'll explain why. So several years ago, my office neighbor at University of Chicago, Nick Feimster, came into my office and he said, Kate, his research area is in broadband, in access networks. It's called access networks these days. And it's an important research area that makes sure that we understand how to provide broadband the best, right? And there are, of course, technical questions in there. So what happens in the conditions of oversubscription, or how does broadband behave over different fabrics or different providers or things like that, but also policy questions, right? So why is access to broadband in this neighborhood different than in this neighborhood, right? Is it the case that some neighborhoods are privileged, so to speak, in access to broadband? And of course, broadband is it's a basic utility these days, right? So it's a very important question to answer. So he's very good at measuring broadband, and he said, well, I would like to deploy a lot of devices nationwide. Can you make it work? Can you make those devices work? Can you make sure that we can deploy them and scale and they're going to be working? And you have this Chia-Edge thing. Can it be used to support a large observatory instrument that measures broadband nationwide, right? So we said, yes, we're going to make the Chia-Edge a little bit simpler, because what happens is Chia-Edge was developed for computer scientists, right? So people who are relatively savvy in how to configure those devices. But he was talking about deploying them to people who are not very technically savvy, right? Deploying them nationwide in various different neighborhoods. It had to be as easy to plug in, to install, as it is to turn on an iPhone. So we said, yes, we're going to simplify it a little bit. We're going to take away some of the function, but add simplicity in its place. And we're going to deploy 1,000 devices nationwide to measure broadband. And about 18 months ago, we managed to acquire 1,000 devices. So I wrote a proposal, create a new project. The project is called Flotto. We're going to have an URL for that later on. I created a project that acquired 1,000 devices about 18 months ago. This is what those devices look like, roughly speaking. You get a box that gets shipped to your home. In the box, there's going to be power supply, there's going to be a Raspberry Pi, and there's going to be a way to plug it into a router, a cable to plug it into a router. And we started deploying them, right? Started deploying those devices. But how do you manage 1,000 devices like that deployed nationwide, right? So you have to manage them in some way that allows you to upgrade those devices, deal with security vulnerabilities or whatever else without physical access. You also have to be able to, if something happens with the device, to have information about the device at your fingertips, right? So just to give you an illustration, we had a deployment once where the cat was playing with the Ethernet cable, was pulling out the Ethernet cable all the time, and people had to call the person, hey, well, your cat was at it again, please replug the device, right? So we had to, and all of that for 1,000 devices, right? So some sort of alerting infrastructure and so on and so forth, right? So it's very different than managing 1,000 nodes in a data center. 1,000 homogeneous nodes in a data center, they are homogeneous, they act as one. These devices, even though the hardware is homogeneous, they are in different networking contexts, in different security contexts, and de facto, they behave as very different heterogeneous devices. So anyhow, again, back to the principle of we like to build on mainstream. So we built this device management layer on a system called Open Balena. It's an open core offering of a commercial infrastructure, which worked very well for us. But it's open core, right? So there's scrutiny on that. It's also robust, reliable infrastructure with good support for all the kinds of security concerns and update concerns that we've had. And as before with Chameleon infrastructure, we also adapted this infrastructure so that there is, some of this infrastructure and some special sauce. So for example, we developed a dashboard that allows us to, drill in to specific device collections and then ultimately specific devices to fix them and manage them and so on and so forth. And we added federated identity login and various other features, just as we did in Chameleon. But that was that allowed us to manage devices. In order to now manage computation on those devices, right? So in our case, computation is running broadband tests. The broadband tests go into a Docker container that gets deployed on those devices. Why? Because when you manage the devices, the operations are not enough. The layer of operations is not enough to support timed execution on those nodes, right? To support timed execution, or as in our case, periodic execution, we need to be able to deploy something more lightweight, right? If you timed execution on the device level as well, I need to upgrade the system, queue up that upgrade over 1,000 devices, sooner or later it will happen. But we don't want sooner or later. We want to run broadband tests every hour on the hour, let's say. And we also want to provide fine-grained management of what runs on those devices. So for example, you run tests generate data. Now you need to upload this data to some central service. But you can't be uploading this data at the same time when you're running the broadband tests, because that would interfere with the tests, right? So you need to schedule those two actions such that they don't take place at the same time. There are other applications where you don't have that constraint, right? You might have different constraints. So you need to be able to schedule things in specific time slots. So this application management layer allows you to deploy applications in Docker containers. That's the Chia Edge principle there. And it allows you to schedule them in reasonable ways for their execution. And like I said, those tests, or, it doesn't have to be broadband tests, but whatever application you have produces some data, and that data is then uploaded to a central service that is running in the cloud. And from that central service, you can use something like Grafana or some other data visualization or data analysis. You can run it on Chameleon data center resources, depending on what you're doing with the data, to look at this data. So now we were talking about change, right? Chameleon is all about change. So how can I change? How can I adapt this instrument to suit my use case? So one way is, and I always compare this to a telescope, right? And you can answer different kind of questions with a telescope by pointing at a different area of the sky, right? I look here, I'm investigating something else. It's the same thing with the devices, right? So we deploy them in one neighborhood to measure broadband in one neighborhood. We deploy them in a different neighborhood to measure broadband over there. We deploy them in the city to experiment with urban broadband. We deploy them in the rural area to experiment with rural broadband. So you just vary deployment scope. You can vary hardware. You can combine these devices with IoT peripherals, right? Internet of Things peripherals, like GPS, for example, global positioning system that allows you to synchronize clocks at a very fine grain, for example, or with a camera, not for broadband, but for other applications. You can write different applications. So already with broadband measurements, there are many different applications that measure broadband. And those broadband tests evolve because scientists measure broadband and then they say, oh, if only we could measure something else, right? Or we're not measuring it in the right way. We need to measure it differently, right? So the thought, the thinking of how to measure broadband evolves as we encounter different problems in the wild, right? So we want to write a different application, put it in that Docker container, deploy it, and off we go. In data aggregation, you can aggregate the data in different ways. You can just collect it, or some people who work with federated learning, they aggregate the data by combining models. And then, of course, you can ask different questions of the data. So to give you an illustration of how we did this all with Flotto, so we're deploying 1,000 devices nationwide. We're deploying them over different neighborhoods. We've got 2 different neighborhoods in Chicago where we study the impact of devices there, in Milwaukee, in San Rafael, but we also have smaller deployment that answer specific policy questions. Another way we adapt this instrument is by developing new measurement applications. So Netrix is the package that my colleague Nick Feimster and his team developed, right? So they measure broadband one way. But there's another group, MLab, called MLab, and they have something called Measurement Swiss Army Knife, and they measure broadband different way. There is the Radar Toolkit measures broadband, whether it's good for telehealth applications, for example, right? And so on and so forth. So we've had a deployment of the different devices, and on the right there, you can see the picture of our deployment map. It's an interactive map, by the way. If you go to that URL, you can zoom in and see where those devices were deployed. We've got a data set that has over 13 million data points at this time, spanning different providers, different technologies. All of that data is available on our website. And the question is, what are the results, right? What is this data good for? So I've got a couple of policy examples here. So for example, on Beaver Island, and we were sort of measuring, what it's like to have the worst internet coverage in the nation. But we used a short-term deployment on Beaver Island of our devices that was used to formulate an area challenge to the FCC, Federal Communications Commission, which led to reassessment of broadband coverage for the whole island, right? And similar in Marion County, we were also able to show that 1/3 of sampled households were below the federal threshold for broadband, right? So those are specific results that were obtained using the devices, using this instrument to affect change. We're now moving on to measuring rural wireless. Rural wireless is a different problem than urban wireless. In urban areas, the problem is, generally speaking, oversubscription. In rural areas is just, there isn't enough subscription in most cases, but people measure the broadband differently. So for example, in cities, we are able to get away with ping pong latency. In rural areas, they want to measure point-to-point latency, right? And for that, you have to synchronize clocks. So I alluded to that earlier. You need to add a GPS device to synchronize clocks, right, at a fine grain. So in rural areas, they're also interested in putting those devices on buses and farm vehicles and measuring as they go, right? Because there aren't otherwise many measurement points available in the rural areas. That means you record the measurement, you record the location. So this is, we had a student last summer who was investigating a little bit, doing some investigative work for how this instrument now would have to be adapted to support rural measurements, and that's his work. We're also working with people using devices to bring measurement and computation into earth sciences, right? So NCAR, of course, is a Chameleon partner. We're partnering with a group there that is developing a project based on 3D printed weather stations, right? So they have weather stations, put them in a 3D printed enclosure, and then those weather stations generate data And we're enhancing that system to provide various different peripherals. Similar system for marine biology in Florida, right? So marine biologists are interested in conditions that are available to marine wildlife at any given time. We put infrastructure into buoys that they deploy. The infrastructure measures various interesting things about the environment, and we collect the data. Another example of how Chi@Edge can be deployed is a case study of a project called AutoLearn. So a couple of years ago, we had students working on a project suggested by one of our users, a user out of Rutgers who teaches machine learning, AI and machine learning to kids by using autonomous vehicles. It's a fantastic curriculum that he developed, right? That is composed of 3 phases. One is collecting the data, right? So you can collect the data by driving the car manually. Then once you have the data, can use cloud resources to train this data on those cloud resources. And then you can validate your research by having the car drive on its own, right, based on the models developed. And interesting thing there is that the package that this user developed contains not just those support for the various experimental capabilities, but also simulators, right? So you can simulate the data by driving a simulated car, and you can then simulate how the car will drive once it drives based on models, right? Based on that, you could develop digital twin. So it's an infrastructure framework that lends itself to many interesting extensions. And a couple of years ago, we had a few students that were porting this package to Chameleon. So the user was already using Chameleon, but he's got his own cars. We were porting it to cars that are available commercially on Amazon, right? So for $200, $300, you can buy a car like this. And there are many, many other projects in federated learning. So we've got a map here of a student who deployed various edge devices over the campus at University of Chicago. We've got precision architecture, soundscaping, and so on and so forth. So just a few words now about what shared infrastructure enables you to do. So once everybody has access to the same resources, it's possible to do interesting things, right? And we sort of coined the notion of practical reproducibility. So we all know that reproducibility is a good scientific practice, but can we make reproducibility a mainstream method of scientific exploration? Because if we could, that could have many benefits, right? So imagine that you go to an ACM digital library, like you do right now, to look at papers, right? But you have something like this that allows you to find somebody's experiments and replay them. And if you could do that, right, you replace somebody's experiment easily. Easily is very important because everything takes time, and that time is taken away from your research, right? So if you can replace somebody's experiment easily, then maybe you can inject some other things into that experiment, come up with a new result. Or maybe you can take that experiment and teach your class based on this experiment. Or maybe, right, just maybe, you can look in that repository not for results, not for what's newest, let's say, in P4 experimentation networking, but for methodology. How do I structure a P4 experiment, right? So you can look for various different things. And I think it would allow people not only a more intuitive grasp of science, but it would also allow the science to proceed faster. And in Chameleon, that Chameleon is an open platform, right? So that means that it's no longer the case that I can experiment with machine learning because my university has a cluster of GPUs, but you can't because your university doesn't, right? Now, everybody has a cluster of GPUs, everybody can access it. But also in Chameleon, what we noticed is by virtue of the fact that it's a cloud and not just your own computer, you have to, and you're reconfiguring remote resources, you have to be a little bit more formal about how you reconfigure them, right? So you have to create an image. boot from that image. And our users created a lot of those images, right? So in practice, this goal of practical reproducibility should be within reach, right? But it's not quite. Packaging the experiment is still a little bit difficult. And we don't really have a shared repository where people can go and share those experiments. But this is something that we're experimenting with solving in Chameleon, right? So we provide integration with Jupyter, we provide various orchestration methods, facilitate packaging experiments. And then we're also working with various reproducibility initiatives to make the papers, the experiments that people packaged for those experiments live a little bit longer. And we've got a repository called Trovi, where you can find those experiments and you can reproduce them. And people do use them in classes and reproduce them for various other reasons as well. So we've got a little graph of how much people were contributing, how many of those artifacts. And right now it's relatively modest, just a couple hundred artifacts that people contributed and work on them. But it is something that has been taking off recently, has been getting more popular recently. And of course, as this happened, we are improving Trovi and improving what we're doing for packaging. Okay, I'm running a little bit slow here, so I'm going to conclude. I'm just going to say, so some time ago, David Patterson wrote this lovely little editorial where he said, for better or worse, benchmarks shape the field. And in that editorial, he makes a point that we need something like a benchmark, well, first of all, to provide a common denominator between research that people do so that we can compare it, right? Because if you use a benchmark and I use a different benchmark, then we can't compare. What are we going to talk about, right? We don't have a common denominator. And then he goes on to say that if the benchmarks are good, in other words, they reflect the issues about which there is a debate in the field, then they really advance the field. Because the comparisons they provide, the common denominator they provide is relevant. It stimulates discussion. And if they are not so good, then the debate, the progress in the field kind of goes down. It's not good. And what I'm trying to say is that test beds that support research, like Chameleon, they're more than benchmark because, first of all, they provide a critical ability to deploy, observe, measure, and record various phenomena, right? So if you think of an experiment, you just think about it, and you can't enact it, you can't validate your hypothesis, right? So they're a critical vehicle of research. But secondly, a test bed also provides a common denominator, right? It provides something that allows you to share. If I have an image, if I encapsulate my environment in an image, I can give you that image and you can replay my experiment more easily. And just lastly, that once we have those test beds and once they provide a vehicle for stimulating community debate by providing this common denominator, we also need to evolve them, right? Give them a means of following the debate. Okay, and this is all I have, so I'm going to shut up now, and I really hope somebody has some questions.
Yeah, thank you very much, Kate. There are questions indeed. We have a first question. You as a young researcher with a limited budget, does Chameleon help me as a member of a university to extend my federated learning model for my distributed computing research?
If your research is in computer science, then the answer is yes. Now, Chameleon is an American infrastructure, right? If most of the users of Chameleon came from outside of the US, I think it would be problematic. So we're kind of saying, when you apply for a project, please let us know who in the US you collaborate with. I would say, especially if you're a member of the Discover US project, there's no problem who you collaborate with, right? If in doubt, just put my name down, right? So we're trying to ensure via those means that the projects that join Chameleon from outside of the US are legitimate projects, right? And it's partly for resource sharing reasons, but it is also for security reasons. We do validate the provenance of our users, and we actually had one incident in 10 years when we had some malicious users get on the system. So it's partly a security reason. But by all means, right, everybody here is welcome to come and use Chameleon. I would be delighted to see what you guys come up with.
Okay, the second question, in fact, was the same, basically. Then there is another one from David Valenson. So great presentation. I'm curious, what specific component or aspects of Chameleon are you most proud of?
It's so hard to choose. I have to say that I'm the first thing that pops into my mind is really the community, the community that the project created. And I have to say it's because it's the most fun, it's the most stimulating and the most motivating part of our jobs. So interacting with our users, understanding the sometimes completely crazy ideas that they have and things that they want to do is, I would say that's most what I'm proud of. On a technical level, I have to say, most recently, probably the G&Edge infrastructure. Also, the fact that we managed to reduce the complexity of the system to the point where it's possible to deploy and operate systems like this, much more easily. So there are many technical, hairy things, many interesting technical problems that we managed to solve. And of course, I'm very proud of that. But overall, I would say creating this amazing community that does super insightful research every day is the most wonderful thing.
Okay, so thank you very much, Kate. Again, thank you also to all attendees. Maria, do you want to add anything?
No, just to thank Kate for the nice talk and for all what we have learned today.
Thank
Okay,
you
so sorry, Kate, go ahead.
Yeah. Thank you very much for inviting me. And I should say, if there are any questions or anything that occurs to you after this, please feel free to email me. My mail should be on the first slide, so not hard to find.
With this, I would like to close the session and thank everybody for all your contributions. Thank you, Kate, again. Thank you very much.
Thank you.
Thanks to all. Bye-bye.
Bye-bye.